Let's review the assumptions we've been making when we talk about integration. Remember that we used upper and lower sums to define the integral of a function, and that these sums are really sums of areas of rectangles. For those sums to make sense, though, the rectangles must actually be rectangles. Let's look at two restrictions we've made that guarantee this, and we'll look at them one dimension at a time. First, we've only considered bounded functions, in other words, functions whose range is contained in some interval CD on the y-axis. If we allowed a function to be unbounded, then one of the rectangles would have an infinite height, so we couldn't compute its area, and therefore we couldn't compute the Riemann sum. We can summarize this restriction by saying that we require that the height of each rectangle be finite. Second, we've only considered functions on closed and bounded intervals. If we try to integrate a function on an unbounded interval, then at least one of the rectangles would have an infinite width, and we'd have the same problem we just described concerning infinite height. We can summarize this restriction by saying that we require that the width of each rectangle be finite. A proper integral is the integral of a bounded function over a closed and bounded interval on which the function is defined. All other integrals are improper. Note that we're not saying that a proper integral is one that exists, but merely that it makes sense to talk about the possibility of integrating the function in question over the interval in question. What can we do if we want to drop one or both of these boundedness restrictions? Let's look first at the case of integrating over an infinite interval. Suppose that we want to define what it means to integrate e to the negative x on the interval from 0 to infinity. We need to reduce this to something we can handle, which means a finite interval. So let's look at the integral on the interval from 0 to 5. This we can determine. Let's go further and determine the integral from 0 to 10. We can do the same thing for the integral from 0 to 15. We don't want to stop at any fixed number, though, since we want to go to infinity, and that's exactly what we'll do. We define the integral of a bounded function f of x on the interval from a to infinity as the limit, as b approaches infinity, of the integral from a to b. Note that we're assuming that f of x is integrable on all of those finite intervals, otherwise the integral on the left doesn't exist. Similarly, we define the integral from negative infinity to a to be this limit. Finally, we define the integral from negative infinity to infinity to be the sum of these two integrals. Note that this exists only when both of the integrals on the right exist. Also note that we can choose a in this case to be anything we want, preferably something convenient. Thus, returning to our example, the integral of e to the negative x from 0 to infinity is this limit, which, when we evaluate it, becomes 1. Note that this is an example of an improper integral, since it's not an integral over a bounded interval. Not all limits that result from improper integrals exist, as we can see with the following example. Consider the integral of x from 0 to infinity. This is, by definition, equal to this limit, which is infinity. An improper integral whose defining limit or limits exist is convergent. All others are divergent. Let's turn now to the case of rectangles with infinite height. In other words, functions that are unbounded on an interval from a to b. Riemann integration is limited, so we'll restrict our attention to functions that are unbounded at isolated points. More specifically, we'll consider functions that are unbounded at some point x, but nowhere else on some interval around x. Let's start with 1 over x from 0 to 1. We are actually dealing with two problems at once, since 1 over x is not only unbounded on 0 to 1, but it's not even defined at all points on that interval. We need to restrict the function to an interval on which it's defined and bounded. So let's consider the integral from c to 1. Where c is some small positive number. We can evaluate this integral, and we get a number. What we really want, though, is to define the integral from 0 to 1, and we do so again by a limit. In general, if f of x is a function that is defined on the half-open interval from a to b and undefined or unbounded at a, then the integral from a to b of f of x is this limit. We define the case in which f of x is defined on the half-open interval from a to b and undefined or unbounded at b similarly. To deal with the case in which the undefined or unbounded point is within the interval, we do as we did before and split it into two improper integrals. If f of x is a function defined on the half-open interval from a to b and the half-open interval from b to c, both excluding b, and undefined or unbounded at b, then the integral from a to c is equal to the sum of these two improper integrals. Once again, the integral on the left exists if and only if the two integrals on the right also exist.